So as an example, a particularly simple case, right? As an example, what we may have is a situation where our domain may be such that this may actually be one of our, we may actually have in these two directions, our coordinate axes may be, our physical coordinates may be x1 and x2, right? And then if our face partial of omega e sits nicely in here, right, sub j sits nicely here, it's easy to construct it as a mapping x1, x2 functions of c2, c3, right, as I'm suggesting here. Sorry, that's too big. Okay, in this case, the mapping is very easy to construct. Okay, all right. So at any rate, what we get then is the following. We get minus sum a belonging to this set CAE integral partial omega e sub j NA Jn ds equals minus sum a belonging to this set. Sorry, I realize that at some point I changed this notation to say a sub j. It should be a sub n here. Okay, a sub n CAE. Now this integral over the parent subdomain simply becomes an integral over say Ci equals minus 1 to 1 and some other Cj equals minus 1 to 1, right? Where in the example that I was constructing, I was saying I equals 2 and j equals 3, for instance. All right? So once we have this, we have NA here, Jn, we have the determinant of this lower dimensional map, right? The determinant of the Jacobian of that map properly, and the elemental quantities here over which we are integrating are just dxci and dxcj. All right. Now, when we carry this through, what we get is the following, right? We can now abandon the explicit sum over the local degrees of freedom, A, and instead we go to a vector, right, which now consists of I guess CA1, E, CA2E up to CA4E, right? Because any face will have 4 nodes, right? In this case, or 4 degrees of freedom, right? In this case. And we have here, when we carry out this integral, we end up with essentially a set of components of a vector, right? And we will call this thing f, forget what notation we used earlier, but let's just call these f sup j to indicate that they are coming from the influx boundary condition, okay? And f sup a, sorry, f sub j a1, f sub j a2, f sub j a4. Okay, and this holds for a1 to a4, right, belonging to that set an. Okay, now this is just an attempt to be systematic with giving us a way to think of the set of degrees of freedom that correspond to the Neumann boundary condition. Okay, and also an attempt to point out that yes, indeed, this integral that needs to be carried out over one face of this element, right, can actually be constructed in a fairly straightforward manner from a face of the parent subdomain. All right, the setup may look abstract, but when one has actual degrees of freedom, actual elements, it actually turns out to be relatively straightforward in most cases. Okay, there are some special cases where, for instance, the surface is indeed inclined or doesn't coincide, it is not a plane or does not coincide properly with a coordinate plane, where the evaluation can get a little more complicated. Okay, but the approach is the same fundamentally. All right. As a very last step, one could actually, one could go away from this representation of a reduced vector here, consisting only of the entries corresponding to the degrees of freedom belonging to this set. Okay, one could simply expand it out, right? Okay. Right, so expanding out all, if we expand out to include all the degrees of freedom in element omega e, here's what we get. Okay, we get minus, this is what we'd started out with, actually going all the way back to the integral that we are trying to impose here, right, minus integral over partial omega e sub j wh jn ds, right. This can now be written as minus, let's suppose the first one is CA1E. Let's suppose the very first degree of freedom from this element did indeed belong to the set A sub n. Okay, let's suppose that the next two are maybe C2, C3, E. Okay, so what we have is A1 is 1, 2 and 3 do not belong to this set. Let's see, 2 and 3 do not belong to the set, maybe 4 does belong, A2, E, 5 does belong, right, maybe 6 and 7 don't belong, and 8 belongs. All right, I'm taking a particular case where here these degrees of freedom, okay, so considering a case where local degrees of freedom 1, 4, 5 and 8 are A1, A2, A3, A4. It's this set of degrees of freedom which basically make up AN. Okay, this is the special case I'm considering. Okay, then what this thing would multiply here would be a vector, okay, which would have a contribution fj1, okay. It would have 0 contributions for the 2 and 3 positions. It would have a non-zero contribution for fj4, also fj5, 0 for 6 and 7, and a non-zero contribution for fj8. Okay? So this is the particular example I'm considering in actually constructing this the final matrix vector form, right? In this case, we use only vectors. All right. You will also note that as I was going along with this example, I kept changing actually the particular degrees of freedom which lay on this face, but hopefully that actually helps because it will hopefully force you to think about exactly which degrees of freedom do lie in it and how to write it in each case, okay, by constantly changing the face that I said was lay on this, sorry, the degrees of freedom that lay on this face. All right. So at this point, we are done with assembling all the element level integrals. When we come back in the next segment, we are going to talk about how to put them all together, right? How to assemble the final matrix vector equations. All right.